Hi, this is Alex from devstories.eu. Biopython Fundamentals, Episode 13 of 18. If you try to find a transcription factor binding site using a strict string match, you will miss a vast majority of the real biological signals. DNA binding sites wobble, and proteins tolerate variation at specific sequence positions. To find them reliably, you have to stop looking for fixed strings and start looking for probability profiles, which is exactly what sequence motif analysis allows you to do. In Biopython, you handle this with the motifs module. You start with a known set of aligned sequences that represent your binding site. Let us use the classic TATA box as an example. You might have a handful of known short sequences like TATAAA, TATAAT, and TATAAC. You define these as standard sec objects and pass them as a single list to the create function in the motifs module. Biopython takes this list of instances and packages them into a single motif object. The immediate result of creating this motif object is a count matrix. At every position along your sequence length, Biopython tallies the total occurrences of A, C, G, and T. If you look at the first position of our TATA box examples, the count for T is 3, and the count for the other 3 letters is 0. This matrix is the literal foundation of all downstream analysis, but raw counts have a severe mathematical limitation. If a nucleotide never appears at a certain position in your small reference sample, its probability becomes an absolute 0. Later, when you multiply probabilities to score a sequence, a single 0 wipes out the entire score. To fix this vulnerability, you convert the count matrix into a position-weight matrix, or PWM. Here's the key insight. You generate the PWM by applying pseudo-counts. A pseudocount adds a tiny baseline fraction to every possible nucleotide at every position. It mathematically acknowledges that just because you haven't seen a cytosine at position 2 yet, that does not mean a substitution there is biologically impossible. By smoothing out the zeros, the position-weight matrix turns your raw tallies into robust probability distributions. Probabilities alone are still difficult to use for sequence scanning. You need to know if a stretch of DNA matches your motif better than it matches random background sequence. You handle this by converting your PWM into a position-specific scoring matrix, or PSSM. The PSSM calculates log odd scores based on a background nucleotide distribution. It compares the probability of a letter appearing because it's part of your motif against the probability of it appearing purely by random chance. A positive score means the sequence actively looks like your motif. A negative score means it looks like background noise. Once you have your PSSM, you can hunt for unannotated binding sites in a long target DNA sequence. You call the calculate method on the PSSM and pass in your target DNA sequence. This method effectively slides your motif across the entire target, scoring every possible window of that length. It returns an array of numerical scores representing the log odds value at every sequence position. You iterate over these scores and look for values that cross a defined strict threshold. If the score is high enough, you've likely found a functional TATA box. A strict string match demands perfection, but biological systems operate on probability, and moving from raw counts to scoring matrices captures that reality. That's all for this one. Thanks for listening, and keep building.